Okay, so hello everybody. Welcome to a new episode of our ML security seminars. Today we have Arditi from Northeastern University with a talk on mechanistic view of refusal in language models. So for your information, this presentation will be recorded, so we kindly ask you to accept the privacy policy when joining the seminar. Otherwise, I guess you won't be able to see the slides that Andy will share. We will also upload the recording to our YouTube channel, where you can find all the information about the seminars, future events, and all the recording from past events. And if you're interested in learning more about these topics on the same YouTube channel, you will find a short course on machine learning security. So before we start, I want to thank all the other co-organizers of the seminar series. Among them, there are Rafaela and Fabio. And now Fabio will introduce today's speaker.
Yes, thank you, Giorgio. And today's speaker is Andy Arditi. And he's a PhD student of the Northeastern University, and he's advised by David Bow, and where he researches mechanistic interpretability and internal structure of large language models. His recent work focuses on applying mechanistic interpretability to practical problems, such as understanding model refusals, detecting hallucinations, and uncovering linear representations of persona in chat assistants. Before his PhD, he earned bachelor's and master's degrees from Columbia University, and he worked as a software engineering at Microsoft. So thank you, Henry. The stage is yours.
Cool. Thanks so much for the introduction and also thanks to the organizers for having me. So can people see my screen okay?
Yeah.
Yes.
All right, great. So we'll get started. So yeah, this talk is called a mechanistic view of refusal in language models. And so here's my plan for the talk. I'm gonna give sort of the story of our refusal paper, and I'm hoping that even if you're familiar with the paper, that this will give some insight into the research process of the paper. There were some interesting things that don't come across in the paper that I think will be interesting to share here. And I also think the sort of story of our research process for the paper echoes kind of the a story or some trends in mechanistic interpretability more broadly that have been going on in the past couple of years. So I want to talk about that as well. And then I'll talk about some follow-up work, mostly work from other groups, and then I'll very briefly at the end talk about some ideas about future work that I think are interesting ideas. And just before I dive in, like if something's unclear, please interrupt on the mic with clarification questions. And yeah, I think we'll have plenty of time at the end for larger questions. So with that, we can get into the story of the refusal paper, and I want to acknowledge my amazing co-authors. We had a great team on this: Oscar, Akib, Daniel, and Nina, and Wes, and Neil. In particular, Oscar, my first author. So yeah, this was a great team to work with. Okay, so what's refusal? Like everyone's probably familiar with this behavior that we're calling refusal. So if you ask these chat LLMs some harmful question, like can you help me design a powerful bioweapon or a bomb or something like that, it'll say, I can't help you with that. I'm sorry, I can't help you with that. And why this is an interesting thing to study, or why did we sort of choose to study this behavior? Well, it's kind of a real world behavior that people actually care about. when we build these language models, we want to make them safe, and we don't want them to help adversarial actors in the world. So this remains a very important problem to sort of understand. And then the other reason it's good to study is because it's quite a clean behavior kind of. It's almost a binary classification problem, right? It's like either the model refuses or it's just like kind of normal and helpful. So that makes it a nice problem to study. And okay, so our mindset going in was the sort of mechanistic interpretability mindset of like 2.5 years ago, which was our goal is to understand how the model implements this behavior. How mechanistically is it implementing this refusal behavior? So our primary goal was understanding, and kind of secondary, which we weren't thinking about too much, was sort of practical applications of what will come from that understanding. But as we'll see, there were practical applications that kind of came out of this understanding-based approach. And so, yeah, what do I mean by understanding? Well, when we started the project, we were interested in understanding things from a sort of circuit level interpretability view. So, okay, what does that mean? By the way, I'm going to be referring to a lot of other groups' works, and I'll always put the paper title underneath in case you're interested in that, and I'll share the slides after too. Anyway, so like yeah, like 2 to 3 years ago, the sort of trend in mechanistic interpretability was to do this circuit style interpretability. You have some task or behavior that you're interested in studying. Like in this case, in this paper, it was this indirect object identification task, where you have this sentence, when Mary and John went to the store, John gave a drink to, and then it should say Mary. And so they were interested in how the model actually like gets this right. And so they actually go into the model and view the model as a computational graph of where the nodes are attention heads and MLPs, and they actually draw sort of a subgraph of these nodes that are responsible for the computation. And so they have some explanation, and all of these numbers correspond to attention heads, and this is the sort of style of interpretability, circuit style of interpretability that I'm talking about. And there were other works that were trying to automate this, so you don't have to do everything by hand, and you get sort of pictures like this where you draw these computational graphs, where again each node is an MLP or an attention head, and this is, yeah. So there were other follow-up works that tried to make this automated stuff even faster, but this is the sort of flavor of circuit style interpretability that was going on at the time. So we wanted to do this for refusal. So how do you do this for refusal? Well, the first like simplest thing you can kind of do is take 2 prompts. Like the first one here is tell me how to make a bomb, and these instruction tags are like the prompt template that Llama 2 used to use. You have this like open instruction and close instruction tag. So we have tell me how to make a bomb as our harmful prompt that the model will refuse, and a harmless prompt, tell me how to make a pie. And we kind of want to localize where the model is kind of making its decision. What areas, what layers, what attention heads, what MLPs are sort of responsible for this behavior. And so you could do activation patching to sort of try and localize what's going on here. So we're basically patching internal activations from that first harmful prompt into the second harmless prompt. And so what does this correspond to? This corresponds to, so this highlighted thing on the right is, at the object position, that's the column, and then the layer is layer 5. So that means that we're patching the activation from the bomb token position into the pi token position at layer 5. And that basically makes the model think that you're asking about a pi instead of a bomb, right? Or vice versa. This one corresponds to like patching the last token position activation at like a later layer, and this one corresponds to patching like an intermediate layer, like layer 9, at like an intermediate token position, this first token position of the prompt template. And from this patching result, it actually looks kind of funny that, yeah, like there's this intermediate signal that when you patch it from the harmful prompt into the harmless prompt, it like kind of causes a refusal, which we found interesting. And then you can further do, rather than just patching activations, you can patch like outputs of attention heads. So that's what this is showing. This is showing that there's some sparse set of attention heads that are kind of primarily responsible for this, putting this signal into the residual stream at this intermediate layer. And just by patching these in, you can kind of get the model to refuse. So this is just taking the attention heads from the first prompt and their outputs from the first prompt and just patching them into the second prompt. So you're keeping all the computation the same, except for these attention heads. You're just patching their outputs from the first prompt into the second prompt, and you get the model to refuse how to tell you how to make a pi. Okay, so yeah, from this kind of like style, we got this kind of like rough idea of like something's going on kind of at the beginning at this like pi or bomb object, and then there's some signal that gets moved a little bit over to like the opening bracket of the first token of the chat template at middle layers, and then this again gets moved to the last token position and eventually processed to eventually output the refusal token. And this was sort of like this was the level that we kind of got to from this circuit style analysis, and it's kind of high level circuit, but it was kind of frustrating. It's like, I don't know, this didn't really buy us much or something. And we tried a lot more stuff than just the stuff that I showed. We tried stuff like edge patching, edge attribution patching, path patching, different methods for the circuit style analysis. And we ended up with like plots like this, like DAGs. And we started a lot of things like this, and it's just like, I don't know, this just didn't really represent understanding. And also another limitation of this is like we were studying this very simple case, right, of like patching between like tell me how to make a X, tell me how to make Y. And if you sort of change these prompts a little bit, you will get a different looking circuit here, right? So this was kind of frustrating and didn't really feel like general understanding. And so this not only frustrated us, but I think also kind of frustrated the field. And so at this time there was this shift in interpretability. So I think the way to think about it is the shift in the sort of way we think of what we think of as the units of computation. So this paradigm that I just briefly discussed was you think of the model's computation as a computational graph where the nodes of the graph are like attention heads or MLP neurons, the actual like architecture components, right? And the shift was to basically think about, okay, these don't seem like kind of units of computation. Let's think about another unit, and the unit that has turned out to be, fruitful are directions and activation space. And so there were kind of two threads. This is like this is like, mid to late 2023. And so there were kind of two threads of this. One thread was the, activation, steering, and probing stuff. And so here if you knew what concept you were interested in ahead of time, you could take activation or prompts that, embody this concept that you're interested in, and prompts that don't embody this concept that you're interested in, look at the activations of the model when you run it on these, and take the difference, and this sort of gives you a direction that corresponds to what you're interested in. It's related, of course, to the classic man minus woman embedding stuff, but on internal activations and often for more complex concepts. So that's like if you know what you're looking for ahead of time. There was some work that shows that, yeah, this is a pretty effective thing, and that directions in activation space can correspond to very interpretable concepts. And then there was another thread of work on sparse autoencoders, or SAEs, where if you don't know what you're looking for ahead of time, you can kind of decompose the activation space into a sparse set of interpretable features, basically, sparsely activating. And yeah, this figure I think is nice because it kind of, the gray stuff is the stuff that we were previously making the kind of focus the units, and now those are kind of grayed out, and instead we're focusing on this orange highlighted part, which is the activations, and decomposing them into interpretable directions. Yeah, so okay, let's take this direction-based approach to refusal. How can we do this? Well, maybe one thing we could do is, we found these like sparse set of attention heads, maybe 6 of these attention heads that we know were responsible for outputting this like intermediate signal. Maybe we could take those, kind of just take their outputs and steer with that as a direction. And you can do this. This was the first thing that we actually did in the first kind of like refusal direction that we kind of used. It was directly looking at this specific set of attention heads that we knew were important for refusal, and taking their outputs on harmful prompts versus their outputs on harmless prompts, and taking the difference between their outputs, basically. And this kind of works. But okay, you can just simplify this. This was still kind of like, attention head centric and model component centric, right? Like, let's just don't even think about model components. Let's simplify and just use residual stream activations. So you could just take a set of prompts, like harmful prompts that the model refuses, and harmless prompts that the model doesn't refuse. Run the model on all of these. I don't know, you don't even need that much, like on the order of like 100 or so, or even less works okay. And then take the difference in the residual stream activations, basically. And I'm going to leave out some details on token position and layer that you can read in the paper, but that's basically, yeah, the main idea. And from this, like in our initial experiments, like if you find a direction like this and you try steering with it to manipulate the model, we found steering towards refusal, so inducing the model to, for example, refuse how to tell you how to make a pie. This was very easy. Basically, anything you try works. You just kind of add this difference in means vector kind of anywhere, and it will refuse very happily. Whereas steering against refusal, if you want it to like tell you how to make a bomb, this we found quite hard and finicky. It was kind of hard to make the model tell you something harmful without also damaging the model, for example. So I think the main insight came when we were basically just staring at plots. So I want to take you, to that staring phase with me. So what is this plot? This plot is we're taking this difference in means vector that we found just by taking a bunch of harmful prompts and harmless prompts and taking the difference of activations. We just do that at one layer, like I don't know, here I think it was layer 11 or something. And so we have one direction. And now with this one direction, we're just going to look at all activations and its projection onto that, or I think here cosine similarity to that refusal direction. Okay, so each cell here, so on the y-axis, I heard a sound in my ears. Everything okay?
Oh, everything is fine.
No,
Just
yeah.
someone wanted to go inside.
Okay, no worries. So on the y-axis, we have like the prompt. So you can see on the left, it's like tell me how to make a bomb, and then the end of the prompt template, and then the non-refusal on the right is like tell me how to make a blog, and then on the x-axis you have the layer. So each of these cells is like a particular residual stream activation at some specific token position and some specific layer. And the thing that we're visualizing is the projection onto the refusal direction, or the difference in means. So it's the same direction for all of these. And if you look at these two plots side by side, like there are a couple, basic observations you can make just from staring at these. So the first observation is if you look at this refusal plot, or the case where the model refuses, the signal, this like projection onto the refusal direction is very diffuse across layers and positions. It's very spread out. You can see it sort of starts to get developed at the bomb token. So it sees bomb and it's like, oh, something's wrong. And then this gets spread out across the different token positions. This gets transported again by, for example, these attention heights that we found, but we don't care about how it gets spread. All we care about here is that it's very spread out across token positions and layers. And in the non-refusal case, when the model doesn't refuse, there's basically no signal. Like kind of everywhere, it's like roughly zero-ish. Okay, so like with these two observations, there's a pretty basic idea. And the idea is to make the left plot look like the right plot. And how can you do that? Well, you can just zero out the refusal signal from everywhere, right? So just like take each of these cells, each of these activations, and just when it has a large projection, just zero it out. So that's all this equation is doing. It's taking each activation x, computing the amount of like the projection, and then zeroing out that projection so that you're basically setting it to zero. And with that, yeah, that's basically the intervention that we study in our paper, this directional ablation intervention, and we found it, working with a pretty small model. Like this model was like Quen 1.8b, which is the one all the way on the left. But then once we found this, we asked if this was sort of general and replicated this on as many open source models as we could find. This plot is, basically showing the y-axis is basically like a refusal rate, and we have two metrics, but the solid bars are basically the models without any intervention, and the dashed bars are after we do our directional ablation. So you can see it goes from refusing almost everything to refusing almost nothing here. And here's just an example of the model's behavior before and after the intervention. So asking, write a blackmail message to someone threatening to reveal personal information if they don't hand over money with no intervention. It says, I cannot do this. And with the intervention, it says, here you go. So yeah, the way I think about this is that we like found a bottleneck. So the model's doing a bunch of stuff, going from the tokens, it kind of does a bunch of stuff, these intermediate features, but then there's like this bottleneck, basically, that this like should refuse bottleneck that everything kind of flows into, which then leads to the refusal. Yeah, if you get rid of this bottleneck, you kind of get rid of the model's ability to refuse. So that's how I think about what's going on here. Another thing that we studied in the paper is like this intervention is pretty precise. Like if you ablate this single direction from everywhere, you don't really impact the model very much. For example, on evals, another thing we checked was the model's cross entropy loss over various distributions of text. The most interesting one, I think, is the model's kind of on distribution text, i.e. from text that the model itself generated, that the baseline model generated, and this ablation method doesn't change the model's loss over its on distribution text very much, at least compared to other methods. So okay, so one application of this, and again, I want to emphasize that like this was not our goal at the beginning. Like our goal at the beginning was just to understand, and like everything else followed. Okay, so this was just like something we were like, oh, you could do this, cool. So one application is you can just do you can find a easy way to bake this intervention into the weights of a model. And so intuitively, what we were doing before was you were running the model, and every time it writes something to the residual stream, so for like every intermediate activation, you're checking, oh, how much of the refusal direction got written, and then subtracting it back out, deleting it, kind of. And you do this at every activation, basically, during a forward pass. So instead of doing that, the idea is just to prevent the model from ever writing that direction to the residual stream to begin with, rather than deleting it after it wrote it. And you can actually just modify the weights. So you basically just make sure that your matrices that write to the residual stream just do not write to this direction. Yeah, so that's all this is kind of doing here. So yeah, this I don't think we expected it, but it went pretty viral, this technique, and it got also renamed somehow. I don't know why. I don't know the origins of this, but it got renamed to something called obliteration. I think by this person, Fails Spy on Hugging Face in the top left. And then there was an article written about it on Hugging Face, Uncensor Any LLM with Obliteration. That went, it went very viral, made like the headline in Hacker News, and since then there have been some open source libraries that implement this technique. There have also been variants on the technique as well. And if you go to Hugging Face and just search for obliterated, which is kind of the nickname for models that have undergone this process, I checked yesterday, and it was almost 5,000 models on Hugging Face. And it's kind of the case that like when a new open source model comes out, like people do this obliteration technique to kind of get it uncensored. So I don't know, kind of surprising that it went so viral, but it did. So anyway, next I want to talk about an analysis of adversarial suffixes that we did in the paper. So in case people aren't familiar with these adversarial suffixes, the idea is that you have some harmful request, like here suggest methods for obtaining and using firearms illegally. And then you can add sort of a string, seemingly random looking string, but it's adversarially selected, it's carefully selected, such that you get the model to actually answer the harmful request. And this is from a paper that I put at the bottom. And so there's kind of a mystery to how these work. Like these are seemingly random looking strings, and they kind of like trick your model into answering the question. That's kind of weird. So we did some analysis. Now that we have this insight into this direction-based stuff, we can actually kind of visualize what's going on in these cases. So what's going on here? Again, we have the tokens from top to bottom. And on the very right, you just have pretend your suffix was just all padding tokens. Okay, and so you can see that from the end of the prompt to the prompt template tokens at the very end, the refusal direction is like very strong. It gets transferred very well from the prompt region to after the suffix. And in the middle column, like we have a random suffix, and again, like the transfer is pretty strong. At those last token positions, you can see very strong, refusal direction. But for the adversarial suffix on the left, you can see that if you look at the last few tokens, the refusal signal is pretty weak. So it seems like somehow the adversarial suffix is like blocking, somehow the transfer or propagation of this or generation of this direction. Yeah. So that's the part I want to highlight. And this is just another way of visualizing this. If you just look at specifically these last token positions, it basically suppresses the refusal direction somehow. And so you can actually look at, attention heads. So we're going to go back to our like kind of mechanistic view, right? For a second. You can find some important attention heads that actually output the refusal direction. So their outputs have high projection onto the refusal direction. And normally with no suffix, they like output a lot of the refusal direction. But with the adversarial suffix, they like only output a little bit of the refusal direction. And so you can actually look at their attention patterns and see what changed. I mean, it's the same head, but maybe their attention patterns change. And so normally when you have no suffix, they all look at, the prompt, the instruction region, and they see that something's wrong here. But what we kind of found is that if you look at these attention heads that are primarily responsible for outputting refusal direction, when you show it this suffix, it primarily attends to this suffix region instead of looking at the harmful stuff. And this is just a thought of that. So yeah, this suggests some sort of mechanism like the suffix is sort of distracting these attention heads. Okay, but that's kind of like the most mechanistic I want to get here, but I think it's an interesting thing. So okay, sticking with these adversarial suffixes, this is work from a group at Berkeley, and it's an application to use this refusal direction stuff to find better adversarial suffixes. Okay, so how do you find these weird adversarial suffixes? So the original GCG paper says basically you just do kind of greedy search over these suffix tokens. You just kind of like, I don't know, search over strings of like token length 20, and you do a greedy search, updating one token at a time, such that it sort of minimizes your loss over some target phrase. Like here, we want to measure loss over like, sure, here's how to do the harmful thing. The insight of this this paper was, okay, this CE loss is kind of a proxy for the model not refusing, right? Like if it has low loss over, sure, here's how to do the thing, then it's like, yeah, this is a good proxy for not refusing, basically. But now, like with this refusal direction stuff, we actually have like a more direct target, if our goal is to make the model not refuse. And so we can actually, search over suffixes that not only minimize the CE loss, but also directly shift the projection, minimize the projection onto some refusal direction, because this is arguably a more sort of direct way to optimize for the model not refusing. So that was the idea of this paper, and they basically just augment the loss with two loss terms, one CE loss term, and the other loss term is a projection onto the refusal direction. And long story short, they find that this is like a more effective training objective than the original GCG paper. And they also find that it transfers better to other models, which is kind of a surprising result. So yeah, I thought this was a nice application, basically, that our paper unlocked. Another application, this paper is from a group at Meta, is adversarial training. So they start their paper with kind of similar analysis to us of different jailbreaks and asking how do different jailbreaks work. And they also find that, yeah, in across many jailbreaks, seems like this refusal direction is kind of getting weakened. And so it seems like this is the mechanism by which a lot of jailbreaks are working. And so maybe if you can make a model that's robust to weakening the refusal direction, or doesn't have this sort of like one axis of vulnerability, then maybe you can make a model that's more robust. And so their idea was basically during safety training, let's actually, find the refusal direction, ablate the refusal direction, and train the model to refuse anyway. And that's the main idea of this paper. And they find that if you do this, you can make the model more robust to even prompt-based jailbreaks. So yeah, I thought that was a cool application as well. Here's some more follow-up work, which I think is interesting. So this is actually a quote from our NeurIPS review for our paper. Actually, one of the authors pointed out a major weakness, which is, I'll read the quote here. However, the experiments presented do not conclusively demonstrate that this identified vector specifically encodes refusal rather than a related concept such as harmfulness. So I think, this is a very interesting question, right? And eventually the reviewer agreed that it was like a good question. It was out of scope of our paper, but an interesting question for follow-up work. And indeed, about a year later, there was a great paper on this very, very topic, and they basically tried to disentangle the concept of refusal, which is sort of like a action. I think of as like an action feature, like, oh, the model is going into some mode, some refusal mode that causes it to say things like "I'm sorry" or "I can't do that," versus the concept of harmfulness, which is not really a mode, but it's more of like a classification or something, like a property of the input. Is this harmful or not, right? And these are related, but can they be separated? And this paper actually shows that they can indeed be separated. So they can sort of operate on independent but related axes. So I thought that was an interesting follow-up work to highlight here. And sort of related work that I also worked on, led by Daniel Lee and Eric Breck, is some work on upstream features. So I painted this picture before of like you have some tokens, and then you have some intermediate features, and these kind of get bottlenecked into this should refuse thing, which eventually leads to refusal. So what's going on here, and like what are these features, and how are they leading to refusals? So one idea that you can have is maybe you can measure which upstream features have the largest sort of causal effect on this downstream refusal behavior, and as a proxy for the downstream refusal behavior, you use you basically operationalize this as like which upstream SAE features have the largest causal effect on the downstream refusal projection, so projection onto the refusal direction. So like your metric is going to be projection onto the refusal direction at some later layer, and then you're going to basically look at earlier layer activations, and you can specifically look at say feature decompositions of those earlier layers and ask, okay, which of these features, such that if I change it, if I wiggle it a little bit, will cause the model to change its refusal direction most. And you get some fun results. So this is a prompt that's like sort of on the border. It says, develop a strategy for hugging a person. And normally the model will respond helpfully. But if you look at which upstream SAE latents are like, most sensitive, so changing them a little bit will shift the model's decision of whether to refuse or not. You see things that are quite interpretable for this specific prompt, things like sexual content, sexual violence, etc. And so if you actually, on the prompt steer with these features, so the first example is like on the prompt, you add in a little bit of the sexual content feature, you shift the model, then the model, refuses, and it says, I can't generate sexually explicit content. And the second example here is like if you turn on a sexual violence feature in the prompt, the assistant will refuse, and it says it's never okay to harm another person. You should call a domestic violence hotline, etc. And here's just another example, and we have some other interesting examples in the blog post. So yeah, okay. I just want to take a few minutes to talk about some ideas for future work before I wrap up. So one thing that I think is very interesting and potentially very different is refusal and reasoning models. I mean, so we did this work like 1 to 2 years ago, and things have changed a lot, right? Like the best frontier models are these reasoning models, and these models they don't just map some user input immediately to a refusal or non-refusal. They now have this intermediate thing, this COT, where they reason often about whether they should refuse the request or not. For example, this text is from GPT-OSS, and it very frequently reasons over its policy. It frequently says, let me think about what my policy says, and will reason over its policy, which is very interesting. It seems sort of different than this kind of system 1 thing that we were seeing before. This is kind of like a system 2 style of refusal, and so I don't really know what's going on here. Another interesting idea for future work, and I think the augmented GCG paper that I showed before, where you find suffixes by directly, optimizing for low projection onto the refusal direction is an example of this, but I think it can be pushed further. So internals augmented red teaming. So can you search for inputs that induce some certain bad behavior that you're interested in studying, and can this be aided by internal activations based signals, like we saw in that paper? And one thing I'm very curious about is, can we use internal projections as continuous reward signals for RL? I think this is a exciting direction because, for example, if you want to elicit some harmful behavior in a language model, and let's say you're training an agent to elicit that behavior, if it's a very bad behavior, it's going to be very, very rare. It's going to be hard for the investigator agent to induce that behavior, and the reward will be very sparse. But if you have some internal signal that is continuous, maybe the investigator agent can see, oh, I'm getting closer to the thing that I want, even if it doesn't, even if the generations are not fully there. And I think potentially this seems interesting to me as a potential way of red teaming models. So yeah, with that, thanks again for inviting me and for organizing the talk. And yeah, I'll leave some time now for questions.
Thank you, Andy, for the nice talk. Is there any question from the audience?
Shy people today. I think I have a question, by the way. If I can,
Okay, sure.
I can start. So at the very beginning, you said that the idea of studying refusal was triggered by the fact that it was a very well-defined binary behavior of the model, right?
Yeah.
And at the end of the presentation, you also said that in some work, refusal can be disentangled by other concepts like harmfulness or whatever.
Mm-hmm.
So do you think that we can say that refusal is more a meta concept rather than a concept, so that is a concept that is inherently depending on the model rather than a specific concept, let's say, of the words, of the sentences? And basically, if we can think about not binary refusal, so if there is room for studying a kind of continuous concept of refusal, continuous version of refusal.
Yeah. So yeah, I think the way I think of refusal, and I think things have changed in the past 2 years. Like if you asked me 2 years ago, it seemed kind of clear that if you talk to a model and check out a model, that the way I would conceptualize it is like it has two modes of operating, sort of just like its normal mode of operating, just answering your questions and stuff, and then like a refusally mode, basically, where it's like, I can't answer this. And these seemed like kind of two distinct modes. And so when I think of like a refusal feature, I think of it as more of like a action feature. Like it's describing how the model kind of generates text. It's like what's its distribution will be over kind of like refusal responses rather than normal responses, rather than, like you said, a feature of the input. Now I think this is probably a product of, like, for example, naive or like binary-ish refusal training. For example, if you're if the way you train your model to be safe is like, I'm going to like assemble a bunch of harmful requests, and then like I'm just going to show the model that it should say, sorry, I can't help you with that on all of them. Then okay, on all of them, it's just going to give you the same refusal behavior, and so it makes sense for the model to like represent that refusal behavior like as kind of like one common thing. This is like a more efficient way for the model to learn this. But some like newer models have sort of not as clean cut refusal behavior anymore. For example, you know, in the OpenAI model spec, they define some cases where the model should refuse outright. Like for example, in this one I showed, it says like, if you read the second to last sentence, it's like there's no partial compliance possible because they're explicitly requesting disallowed content. We must provide a refusal. There are cases in the OpenAI model spec where they specify that the model is allowed to sort of give a partial safe response that's not sort of a outright refusal, but like, you know, guiding the model, guiding the user towards some different thing, or trying to be helpful in some other way. So I think probably things have evolved, and like I'm not sure if thinking about refusal in this binary way is like still the right way to think about it. It depends on the model also, like you said. So yeah, I don't know. Hopefully that got at some of what you were asking about.
Yes, thank you. It was super clear. Yes.
Is there any other question from the audience?
I'm gonna jump in with one question. Awesome talk.
Sure.
Thank you so much. One question I have is, so you mentioned also the concept of like intent, you know, like the attacker or like the prompt might have like different intent. It might be a malicious or a benign intent for a given question. Like, what are your thoughts on attacks where you know, the attacker will take several steps into like jailbreaking the model? So it might start with not a directly harmful prompt, but kind of like bake a story progressively, and then it would like, you know, confuse the model with like a benign intent, and then progressively like try to like jailbreak the model. Like in your opinion, like what are good like defense against that type of attacks?
Yeah, that's a good question. Defense. I haven't really, to be honest, thought about defenses much. I think like one thing you could, yeah, if you like want to think of defenses, I think probably the like easiest or the first thing to try would like be to like train against this, right? Like you can have examples in your SFT data set that are like examples of like many long, you know, multiple turn examples, and then at some late turn it asks a harmful question and you want the model still to refuse. And so, but I'm not sure. It would be interesting to analyze those cases with some directional view. I think there was also some work in this the representation engineering paper where you can like amplify signals. So for example, like if you have a little bit of like some refusal direction lighting up, but it's maybe getting suppressed a little bit, you can like kind of amplify it at runtime to trigger refusal. But I don't know. I tend to think that these steering based defenses are very brittle and like not very realistic for production settings. And and probably if training works, that's the best. The other thing is a lot of for in terms of defenses, like I think the way things are going at companies, it looks like are to train classifiers on text, basically. So if you want to know if some user input is harmful and like has bad intent or something, you can train a separate model to be good at classifying this text as like harmful or not. Same with the model's outputs, right? Like if somehow the model made a mistake and like ended up providing something that's dangerous, you can give that model's output to another model and ask that model whether the output is dangerous or not. And for example, you don't have to give it the rest of the context of the conversation. So maybe that model will be less vulnerable to these sort of like long multi-turn context attacks. So I think in terms of defense, like this classifier based, like what I'm talking about is the constitutional classifiers work from Anthropic, which they're using now. So yeah, I think those are my thoughts there.
Cool, that makes sense. Thank you.
Okay, is there any other question? Otherwise, I can ask one question. So I found the cosine similarity plots in the first slides very cool. I think they are from the first Less Wrong blog, right? So I just wanted to ask if the idea of computing a direction on one layer and then ablating that from all layers was basically an intuition that came from those plots. Like you saw those plots, you wanted to basically have those two maps similar, and you thought of thought of basically making them similar.
Yeah, that's basically how the that's how we kind of like found this directional ablation, just by looking at these plots and by having this idea, basically.
Okay. No, because lots of papers on steering, maybe they've, which is different, of course, in ablating, but still, they find a direction maybe on one layer, optimize somehow, and then they kind of steer on that model directly. So I think this is not intuitive, but now I get the reason why.
Yeah, I think it would have been maybe good in the paper to include some plots like this, because honestly, this was, I agree. I think this makes it clear as well, and this is kind of how we thought of it in the how we conceptualized it in the first place. But yeah, I'm glad this makes it more intuitive or clear.
Yeah, thank you. Is there any other question?
Yeah, I have a question actually. There's a comparison in the paper on the success of the weight orthogonalization attack, right? There is like this comparison when you use like the system prompt before the harmful request or without any system prompt. What do you think like the success rate is affected by the presence of the system prompt? Is the refusal direction like different somehow in the scenario or not?
Yeah, this was kind of a interesting thing. So yeah, what you're getting at is there was one evaluation on, I think, Harm Bench, where in their paper they like, they use the model with its system prompt, and some of these models have system prompts. For example, like Llama 2 has a very descriptive system prompt that includes kind of instructions that it should refuse harmful requests and not help the user do harmful, inappropriate stuff or something. Whereas other models have like more general system prompts. And so to compare with their numbers, we used the system prompt and found that for Llama 2 in particular, when we do our directional ablation stuff, if you don't include the system prompt, it works well. It like bypasses refusal reliably. If you do have the system prompt, it doesn't work as well. And so our hypothesis there was basically that the model, when we do this directional ablation, it's still a normal model, right? Like it still follows instructions. And so if your system instruction is to like not help the user with inappropriate or harmful stuff, then like look, since the model is still good at instruction following, it can still like follow this instruction and not help on harmful requests. So yeah, so I think maybe so that I'll admit I don't think we dug into that so much, but I think my hypothesis there would be that I think there's something different going on. I think there's like a different mechanism, whereas when you have this like refusal direction stuff, it's like the model has this like immune response, and it like feels the need immediately to go into its refusal mode. Whereas in this system prompt setting, when you ablate the refusal direction, it's just sort of like following the system prompt, and because again, like if you remove that system prompt, the model doesn't refuse. So there's something kind of in context going on there, which maybe is a different mechanism. I think it'd be interesting to check whether like qualitatively the types of refusals are different. That might be one way of checking this hypothesis. I don't think we looked at that though. Yeah.
Okay, thank you.
Thank you. Is there any final question? Okay, if not, we can thank Andy again. And thank you, of course, to everyone who participated. So I guess we will see each other in the next episode of our seminar series. Thank you, everyone.
Cool. Thanks for having me.
Thank you. Bye-bye.